All right, so we'll do a difficult topic today. So we're going to solve Burger's equation. Okay, it's a time dependent or non-equilibrium field theory. Okay, so far we did equilibrium field theory. Now this is one example for non-equilibrium field theory. So the equation, it is this. We'll do 1D only, okay? So this is my equation. Let's assume forcing, but is at large scale forcing. So this is a system, 1D system, a box size L, and here we have velocity field. Okay, so it's periodic, assume periodic. Now we apply forcing at large scale. That means maybe I explained this is a set of cars traveling in 1D road. Some are going fast, some are going slow. So imagine there is some kind of current in the road which is forcing the cars also. Okay. Anyway, so this is not going to be very important for us, but I'll tell you a remark on the way. So this is our equation. It has time, so it is time dependent. Okay. Now this is in fact we can show that it doesn't have any pressure term, grad P. If you know fluid mechanics equation, no pressure. So these particles are kind of freely moving particles. Now this is moving fast, and this is moving slow, and this is moving in the opposite direction. This is moving fast and fast, slower, like that. Okay. So what happens is these guys are move fast, and this is moving to the left. So this part we get a shock. So what is the shock? So we have velocity field which is very high in the just before that point, and here the velocity is negative in the opposite direction. So the cars are going there and cars are going here, and they just simply can't move. So there is a pile up. So this is called shock, and you can show that the equation for this solution for this equation in the asymptotic state. If you wait for long enough time, this kind of solution for every point for which the velocity field is the slope is coming down, negative slope gives a shock. This will not be a shock. This will be this point is this point, but there will be a shock here. There will be shock here. Okay. So the shocks are captured by this equation. So I told in the last class is proportional to x. No, x by t I had written, but so mu is the shock height of the shock. So this is equation for one band from, let's say, from here to here. So in fact, in the solution, if nu is finite, small, then this is not sharp. It is smooth function, it goes like that. So it is like this. But if you make viscosity very small, then it's very, very steep. Okay, so these are exact solution. Now from this solution we can compute structure function. What is structure function? I am going to do second order. Ux plus r minus ux whole square. This one. Okay. Now I will not prove it. This is not so important for our field theory course. But in fact, my solution is like this. But it turns out it gets a contribution near the shock, and this we can show it is proportional to r. Okay. Now this has dimension of velocity squared. Okay, and I need to get velocity squared dimension, no? So if you do all the algebra properly, you'll get mu squared by L. This is the formula for the structure function when r is small. Okay, but so there is a condition that this r should be bigger than the shock width. So there is shock here, so the shock width should be bigger than shock width. Okay, now I'm not proving it, but I'm just stating it. But it's less than this distance between two shocks. Okay, so R is the intermediate distance. Now if you have this structure function, then I can get the correlation function. How to get the correlation function? So let's call it u prime, okay, the u prime. So u prime minus u. So u prime squared plus u squared minus 2u prime average. It is mu squared r by L. So I can get a formula for this, the correlation function, which is ux plus r. These are constants, no? This is in fact average kinetic energy. U squared, u prime squared. So this I take to the right hand side. So this is 2u squared minus mu squared r by. Whether there is a prefactor, there is another prefactor which I am not writing. Alright. So now what is the spectrum? So from correlation function you can compute spectrum. This is CR, right? This is just correlation function in real space. Now I did mention this in the early lectures. You can compute the Fourier transform of CFR. So C of k, or which is same as E of k in one dimension. It is integral CR e to the power IKR PR. So it's Fourier transform of CR gives you CK. Okay. Now this is a constant. So constant will be a delta function at 0. This corresponds to mean value, no? And mean value corresponds to which wave number? If I do Fourier transform a signal, let's say we have a sine wave plus a constant. So C plus sine x, sine of r. So if I do Fourier transform, C will be k equal to 0 mode. Right? So in fact fx, fr is fk e to the power ikx dk. So if you put k equal to 0, then I get constant. No? You can do a sum if you. So k equal to 0 mode corresponds to constant, k equal to 1 mode corresponds to sine, e to the ikx, and so on. So this is the k equal to 0 mode, which I don't worry. But this one corresponds to other, it will give higher wave numbers. So in fact it is r mu squared by L e to the power IKR. There is a minus sign. Okay. Now this integral can be done. It's a bit of a problem. Okay. Why it is a bit of a problem? Because R is an increasing function. R is a monotonic increasing function, and strictly speaking, this does not have Fourier transform. Even for a finite box, because R should be, according to the theory, should be square integrable function, and R is not an integrable function. R is in fact going increasing to infinity at R going to infinity. Okay, but we will make the box finite. So my box is this integral is 0 to L, right? My box is only going from 0 to L. So we can compute this. Okay. And now I will just do the dimensional analysis. I am not going to do the full algebra. But what is the dimension here of dr? So mu square by L is a constant, right? Mu square by L is a constant. And what about this object? R dr. So it is r squared. Okay. So r is 1 by wave number. What is the dimension of K? K is 1 by length. So this comes out to be K minus 2. And a constant in front. Okay? The constant in front. The constant happens to be 1 by 2 pi. Okay? So this has been done in a paper by Safman. Safman wrote a many years back, many decades back. It is in 1950s. This paper is in 1950s. Okay? And we have repeated those calculations, but some more new calculation. This is by Alam. I think it's 2022 in the physical review fluids. Okay, so this is the paper which you can look. So I'll forward the paper. Okay, I will put in the WhatsApp. Okay, so this is the spectrum energy. Now, of course, we want to do field theory, so we want to compute the Green's function and correlation function. Okay, that's where I'm going to. And I'm show you that they are different and they are computed differently compared to Wilson theory. Everybody is with me so far? It is exact. I skipped some steps, but you can do it yourself. Now, so this is shock. Now, with time, this height keeps decreasing with time because there is a loss of energy. There is a viscous force here, so it is sucking the energy. Where is this term more important? Where this double derivative is large. And which part the double derivative is large? In this plot. What is double derivative here? 0, right? It is 0. Double derivative will be non-zero here. There is a steep turning. Okay, the derivative is changing very fast, so the double derivative will be non-zero. And in this band, there is a strong dissipation. This is a viscous dissipation term, right? Here, the energy is getting killed, the kinetic energy. So this part is viscous dissipation. So the energy is going down, total energy. Okay. So in this system, there is no detailed balance. The energy, in fact, energy is coming right now either from the forcing at large scale. Even if you don't force, this large velocity field, the shock, also has energy. In fact, it's a very interesting case where the energy at this range, there is a large energy that is supplying as well as dissipating. Okay, there is energy at large scale. Well, the shock has energy. That kinetic energy is decreasing. Look, where is the energy maximum? Half u squared. Half u squared is maximum here. And that energy with time, so if you wait for some time, then it becomes like that. The slope is 1 by t. So it goes down like that. Okay, so it keeps coming down, and so this system is not in detailed balance because energy supply at large scale and dissipation at small scale. So it is very similar to what you do in a coffee cup. If I put coffee here and take a stirrer and I stir this, so energy supplied at large scale and it dissipates and goes to small scale thermal energy. Everybody is clear about that? Now it turns out, so we may ask, how is energy flowing from scale by scale? So we are supplying energy at this scale, box size, let's say L. Then there are structures which is size L by 2. Okay, so in fact the big vortex becomes smaller vortex in fluids, not here. Here there is no vortex. In fluid it becomes small structures. Then L goes to L by 4 and so on. It keeps going down. So it is going down in scales. Okay, and it turns out for hydrodynamic flows with only velocity field in coffee cup, the energy supply is constant. Supply energy constant. It can be proven. It is constant. Okay. So this was proved by Kolmogorov. Okay, where Rodion comes from, Russia. So he proved this energy supply rate is constant. Here also energy supply rate is constant. If there is a nice argument, look, where are we supplying energy? At large scale. Okay, so we are supplying energy at large scale. So I'm going to draw this scale. So let's put wave number, okay, 1 by L. This is a wave number K. I supply energy at large scale, right? This is that guy which has a lot of energy. Imagine forcing is off. Let's turn off the forcing. Supply energy, and is dissipating at small scale here. 1 by small scale. Eta, 1 by eta. This is size is eta. This size is eta. In between, there is no dissipation. There is no dissipation at scale here. It dissipates only here. So imagine there is you are driving your car, but the road is very smooth, so car will go with constant speed. But when there are a lot of bumps around or some sand or stuff, so then it is dissipated here. So energy keeps flowing down, but in a scale, it is not in a linear road, not in a car. It is happening in scale, so it is going like that. So since there is no dissipation in the intermediate scale and there is no forcing in the intermediate scale, this is going constant. So this variable energy flux is giving us the idea that energy flow is constant. Okay? Maybe some of it is not very clear, but I'm just telling you that. So example which I give is energy, well, the money flow from the central, okay, Delhi. So Delhi is giving money to states. States are giving energy money to districts, districts to cities and villages. So if there is no funneling of money or nobody is taking it out from and putting in their pocket, this money flow will be constant at different scale. Correct? So that is what is happening here too. So we are getting energy supply at large scale, which is here. This large scale, big shock size. Well, shock is at the given region, but basically there is an energy at this scale, where is the shock, and that is going down step by step to small scale. Okay, and let's try to do this, compute this analytically. So this is our challenge. So we want to compute the Green's function and correlation function for this system. So I can also tell you the energy which is flowing down like this, it can be proven from this formula. So this derivation is there in our paper. Okay, this paper you can look at it in this paper. So flux. So instead of L, I can write as K. It is constant. It is mu cube by L. L is the box size, and this is a factor 1 by 12. So these are exactly calculated. Huh? So this is a nice equation which has exact solutions. For Navier-Stokes equation, we can't get all these numbers exactly. So I should write the name of this equation, Burger's equation. Okay, so let's get all started on computing the Green's function. Okay, so this is the first time dependent field theory. So we write u of x as integral u of k e to power I kx dt. I am not putting 1 by 2 pi because this box is finite box. Okay, for this example I am not putting 1 by 2 pi. So this is 0 to is minus infinity to plus infinity. k is all over. Okay, so I'm going to substitute that here, but I'm going to rewrite this equation, this part as d by dx u squared by 2. Right, this is same as u squared 2, and bring half outside. Bring half outside. Okay, so put ux here. If I take a time derivative, so this is ux t n comma t. So u is function of now this Fourier transform k and t. Earlier this function of x and t. So what happens to the first term? So let's write d by dt of u k t e to the power I k x t. So d by dt will come inside, no? So this is not function of time, this is not function of time, so it is acting on d by dt this way. Okay. Now what about the next term? You should focus on this one. So half derivative will give you what? K, ik. So this is in fact this term will ik. Okay, and then there will be a integral da 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 da. Okay, so this we've done in the past. So I'm just going to state the result. Okay, so you get d by dt of dt plus I k by 2 integral dp. So this will be convolution, no? This u squared will be convolution. Up uq equal to minus nu k squared. Okay, so you can rewrite this d by dt plus nu k squared uk. Sajid, this is visible in the still there. I k by 2 integral dt minus sign. Okay, everybody is happy with this? This is the equation in Fourier space. So what is the Green's function for this equation? So of course, if you put, let's put the nonlinear term to 0. This term is 0. Then the Fourier transform will be of this one will be a Green's function will be inverse of this, right? So this is our linear operator O. Okay, so I define the Green's function d by dt plus nu k squared gk t minus t prime. So what is the source? Only for the linear term, I don't keep the non-linear term. So delta t minus t prime. And so it is a, so the k as well. Yeah, so anyway, let's just, there's no k dependence. This is a delta kick. This is my Fourier transform, Green's function definition. This nu is the viscosity, okay? Nu is a dissipation term, viscous term. Now, so if this term wasn't there, I can easily solve that equation. What is the equation without this? What is the name of this equation? Diffusion equation, right? So we can easily solve it. And the Green's function for the equation for diffusion term is this. Okay, we solved it in the class. The exact solution. In fact, it was there in the exam too, I think, right? Diffusion equation. But what does this nonlinear term do? So if you want to write down the Green's function of the full equation, then this is not the correct way to do it, right? So I need to, this is a nonlinear term, so I can't really easily write Green's function for this. If you want to try, then you can bring it to the left hand side, plus I k by 2, and you can say, well, I'll replace, what did you do here? I replace u by Green's function, no? and the source was made a delta function. So some people do write like this, dp u Green's function. Well, now this is q, okay, so q t minus t prime up. So, but this is the nonlinear term which I want to do it, take into account properly. So the idea is to compute the Green's function. In fact, for the full equation, for this whole equation, in this equation, if I put some perturbation, then what would be the effect for the full equation? Okay, so it turns out, so I'll tell you the answer, then I will derive the answer. Okay, now as I said, it's a difficult calculation, so I'll just tell you the answer. Because of this term, this viscosity will be enhanced, it will be more. Okay. Right now this is a small viscosity, maybe 10 power minus 5, but in the effect of this perturbation, I can show you that nu k squared will be going as the shock height times k. Okay, so nu k is in fact mu divided by k. That is what I am going to show, and that is coming purely from nonlinearity. Now, to give you the example why this is important is the following. Okay, so I did that in the class some time back, but I think it is important to state that example again. So let's erase this part. So by the way, for 5-4 theory, if you recall Wilson theory, we also was changing the coefficient, no? The coefficient r, small r, yes or no? So the two parameters r and lambda, and both of them change with scale. Yes? So same thing happens here too, that nu is going to be changing because of the nonlinearity, and we go to larger scale. Okay, so perfume spread or diffusion of perfume, right? The example which you did in the class. So perfume, if I compute from the diffusion equation, so what is the time scale? L squared by kappa. So 1 meter distance, if I use this kappa, then 1 meter squared, and kappa is for atmosphere is this. So what is the time scale? 10 power 5 seconds, which is very, very large, right? 10 power 5, like you have to wait for many, one full day for the perfume to diffuse. So that is the diffusion coefficient for this equation. But in reality, the diffusion is faster. So what causes the diffusion to speed up? Nonlinear term. What is the nonlinear term in the atmosphere? The term which is plus u dot grad n. Okay, so I'm doing very similar. So what happens if we do this? So let's rewrite that equation. Okay, so in fact I'm going to do exactly the same thing there, but the idea should be clear. So let's rewrite this as kappa k squared. Correct? I bring it to the left hand side, and this will be this term, exactly like this term. Correct? Everybody gets this? What happens to this term? It's a nonlinear term which I take to the right hand side. So it's going to, grad will give you minus ik. Well, I can rewrite this as divergence of n. So this term will be very similar to this term. Not exactly, but similar. You agree with that? Here is u squared, gradient, but here is u divergence of nu. Okay, so you write, in fact, I'm just going to write up nq. So the effect, so the idea is the following. So let's follow Wilson. So what did Wilson do? He divides this stuff in wave number space like this. So this is large k, k is increasing. So at this scale, very large k, only this term is active. At very small scale, kappa is active. But when you keep going to small and small scale, the time keep coming down like this, slowly, slowly, then my kappa increases. So that's called renormalization. Kappa is increasing, and when you come somewhere here, my kappa is very large. And what is the value of kappa at that scale? If I can estimate from here. So the estimate from here will be n by t equal to here u by L n. Right? So this cancels. So t is L by u. L is 1 meter and u is 1 meter per second. So t is around 1 second. So the kappa has increased a lot. So that is what has happened here. Viscosity is increased. Mu is large and kappa in this case at the case length, 1 by length, right? So this is mu times L. Okay, so this is what has happened for this example. Now let's do this computation. This computation is somewhat different. Well, it has some catch. Okay, so that's why I said this is a very not a trivial calculation, but I want to show you how to do this. So this is a nonlinear term, no? This term. So I'm going to write down is a Feynman diagram. So this is UQ. So I should write here. Okay. So we'll assume this UP, UQ to be random fields. Well, here it is not quite random, its shock is not changing much, but assume random. For this calculation, this is that's what people assume. Okay. So, and what is the prefactor? It is ik by 2. Now, following Wilson, if I just follow this, so if you recall, what did Wilson do? So Wilson said, let's make this as less and greater. Less and greater. Now this is what you have to recollect those examples. So I'm interested in getting u less here. Now, so what is by the way, I forgot to write. So convolution means k equal to p plus q. It's not a vector because it's 1D. By the way, q can be negative as well. Huh? So if we have k here, k, so p, q, or it could have k like that. P could be large and q can be like this. Okay, so we have all sorts of combinations, but it's all along 1D. So calculations are not very difficult. Okay, now so here I can get k. So remember this p and q can be in this region, right? To give you k. So let's k is 10. So p can be 5 and q can be 5. It will be in that band. Let's say this is 9. Okay, separation. So I can have this is less plus less greater plus greater. That combination. Now, so this part of the equation is same as before, right? So these are less. So if these terms are 0, if I compute, if I do the convolution, if they are 0, then I'll get back the original equation with no change in u. Correct? No change in u. Is that clear to everyone? If these terms are 0, then I get back the original equation for less, and nu will not change. But these terms do contribute, they are non-zero. And it turns out, if I average them, we assume that less is greater is a random variable, but less is not a random variable. Less does not change, but greater changes. So this gives you 0, but this gives you non-zero value. So we are interested in computing this, greater. Okay? So we can write greater like here. In fact, this is there in our Wilson theory calculation. Now, so this term I'll tell you without proof that if I don't do any expansion, this is 0. Average UP UQ is 0. Why is it 0? Because that requires that Q equal to minus P. Right? This is non-zero only if Q equal to minus P. Yes or no? U star of K mod square, that is not 0. But this is random variable, this is a random variable for different wave numbers, so it will be 0. Okay? So to leading or to 0th order, this term is 0 if I average. But I need to go to higher order. So what is higher order? I do the expansion of U greater P. So how do we do expansion of heat from here? I again use this equation. So what is UP? UP. So this is a Green's function inverse, right? So UP at time t is written as Green's function. This is a time dependent Green's function, by the way. So gt minus t prime dt prime and this source term. A source term, now what is source term here? For P, so I need to write for UP. Okay, so what is equation for UP? Let's erase this one. This is writing very d by dt plus nu p squared u less UP equal to, so please tell me what is going to be. So it's going to be minus I, so this same as this argument, minus I p by 2 integral, what is the integral here? Now I should not use p because p is a variable here, so use a dummy variable. So use a dr ur us. So r plus is equal to p. Okay, so this is my equation for UP. Yes or no? R plus is equal to P. So, by the way, this can be any variable K. Yes, everybody is happy? So here I need to write integral d r ur us is function of what? P prime. Okay, this is a function, this is UP of this is the different value. So what I'm doing here, UP EPT. So when I write T, if so Green's function, this is source. So how do I solve this equation, by the way? Assume this to be the source. UPT equal to Green's function, which is t minus t prime, and source at t prime. So this should be computed at t prime, not at t. So this is at t prime. Okay, I hope I'm following this. So we rewrite this stuff. So in terms of Feynman diagram, okay, now this is what you should know, ik by 2. So this is Green's function like that. This is uq, and now we have two u's. What are the two u's? The ur and us. Okay. So this is what I got, ur and us. So this is ip by 2. The vortex here is ip by 2. Is a minus, so this is a minus sign here. The minus sign here. Plus here, minus sign there. And the minus sign here too. Okay. I hope I'm still understandable. So here now, if I have three u's, this is u of q, this is u of r, and this is u of s. So when I average them, can I get some simplification? So it's possible that if q and r are opposite, then these two can combine and become a correlation function. Yes? U of p, u of minus p is a spectrum, right? So if r is equal to minus p, r is equal to minus q, then this can combine and that will become C of q. Okay? And what about this? So r plus s is equal to p. Remember I had written that r plus equal to p. Now what is r? R is minus p. R is minus q. So minus q plus s is p. So what is s? P plus q. And p plus q is equal to k. So this is nothing but k, which is great. Because I got an equation in the right hand side which has some number here and uk. And k should be less than kn, should be less, okay? So it is less here. So if you follow Wilson procedure, I exactly did this. So we have this stuff, some number. So this is some number a, or let's call it b, u less k. Which is great, no? I mean, I'm really making good progress. Why? Because these objects are b, u less k. So what will it do? So if I take it to the left hand side, then that will change my nu, right? And this equation looks exactly same as before. So I'm going to erase this part. This looks exactly like before, but d by dt plus, so let's put it k squared here. Okay. So nu minus b, or if I put a minus b here, minus b, k square, so this becomes plus, minus comes here, k square, whole bracket, this part. So I get back the old equation, but my viscosity has increased. Okay, so that's the beauty of this stuff. Is it clear to everyone? Okay, so so this is one term, but we have another Feynman diagram. Okay, so this was done by expanding up, but I can also expand uq, right? So what will that expansion give us? So I have Green's function like that and that, and this one is minus ik by 2 and minus iq by 2 and u less q. So there are two terms, in fact. The b involves two terms, one coming from here and one coming from there. So these are integrals. So let's do the integral. So I will erase this part. So I can write down u prime, which is this new one, equal to nu. So k squared. Let's put k squared here. K squared here. So I'm going to copy from your notes. Okay. So this is a correlation function, right? U is a correlation function. So I'll just write down this formula. So this is a 1 by 4. In fact, it's quite easy to see. This 1D, it turns out to be quite nice. K by 4 integral dp pcq plus qcp divided by nu p squared nu p squared. So this is the okay. So there is one more step. Okay, so which I skipped. So there is a time integral, no? So I think it's important to write down. This is a time integral, right? So how do I get it? How do I solve the time integral? So this Green's function. If you look at here, what is the Green's function? If I solve in terms of time, so it is just exponential minus nu k squared t minus t prime. That's the Green's function. Okay. This in fact, diffusion equation has this form, right? Yes or no? Green's function for this equation is that. Now here, this is function of t in t prime. So if you recall, this part was coming from different times, t prime. So the correlation function also gives you a term which is minus nu k square t minus t prime. And there is a correlation function which is called one-time correlation function. Okay, so the thing is, here we have, this is the one time and this is another time. Okay, so we have, this is time t and this is t prime, complex conjugate. Okay, so this one, they are not at the same time. So this is a postulate. We make a postulate that we write this as C of p exponential minus nu p squared t minus t prime. So this is phi p and the other one is q, this g of q. So together that gives us p squared, this stuff. But I do not write nu as a constant, but write nu as a renormalized viscosity. So I make an assumption that when I am doing it here, I am using the full Green's function. Okay. So this is called self-consistent field theory. Okay. So some people, what they do is they start with small without any perturbation or without any change, just bare viscosity, then keep changing step by step. But that is long series, right? So one idea is to, well, I'll assume right now that I was somewhere here, there's a small scale, but then I already have come somewhere here, okay, which is in the already coarse grained state. I'm already in a pretty large scale. And at that scale, my viscosity is already enhanced. So I am in the intermediate stage where I am allowed to do this. So for the diffusion equation, the diffusion at the microscopic level will be 1 micron size, 10 power minus 6 meters. But in this room, the diffusion is 1 meter scale. You should think that I am doing this perturbation at 1 centimeter scale. There, this viscosity is already enhanced. Okay, so that's the whole idea, and we write like that. So this is function of K. And what should be the band here? It is Kn to Kn plus 1. Right, Rodin, that is what formula we get. So this is what we were doing standard field theory. But this has a problem. It turns out Burgers has another problem. Okay. Unfortunately, the example Dhananjay is not here. This is supposed to be his project. This does not give you the right answer. We know the answer. We know that my spectrum, this one, CFQ is what is CFQ? It is mu squared by L 1 by Q squared. Right? I told you the spectrum is 1 over Q squared. There is 1 over P squared and there is mu squared in front, and this is 1 by length. Now I tried very hard, okay, to get this consistent solution by this procedure. So look here, I get 1 over length, mu squared by L, right? This is a prefactor. Mu squared L is a constant. So this will be prefactor. Now this one is not a function of L. So there is a new, of course, well, if I make it not a function of L, then I cannot cancel this L. This side is not a function of a small l, this part, so I cannot cancel this. You understand, the right hand side is function of 1 by L. I can get mu. Viscosity is, if I say, dimension, what is viscosity dimension? Nu k squared. It is dimension of 1 by time, right? This is dimension of 1 by time, inverse time. Okay, I am postulating, let's say, this comes by experience. I am postulating that it will be proportional to this mu, which is shock height. So how do I get time from here? This is velocity by length. So I can multiply this by L or multiply this by K. I can do two things. Yeah.
Nu dash in the denominator.
Nu dash. This one?
Yes, because we defined the normalized viscosity as nu dash. Right?
Okay, but by the way, Rodin, this is for any wave number. It's function of P. Nu dash is changed, so I'm saying nu dash is after I add this. So this is a correction. So this integral, if I do this, we will give me the correction to new viscosity. So nu is a function, so it's okay. So either it is this or that or combination. So I could also make mu square root L K is possible. Sorry, K by, no, I can't do that. So 1 by time, so mu by L, right? So this will be 1 by time. This velocity by length is 1 by time, right? So try this here. This is mu squared by L. If I make this as mu by L, then this side also should be mu by L, right? This is at mu by L, and I don't get that. So what a very interesting aspect of Burgers equation which I cannot explain in a detail, is that this interactions in Burger's equation is between wave numbers of different magnitudes. So there is a wave number, let's say wave number k. So wave number p and q. So k can be much bigger than p. Or k can be of the same order. So these interactions both are very important. For Wilson theory, it appears, okay, I am not 100% sure. So k and p are of roughly same order. So these are local interactions. So for local interactions, I can think of interactions coming from this shell. I can do gradually, shell by shell. So imagine the village people are interacting among themselves, not so much with the city, somewhat with the city, but not so much with the city. So I can post in the structure interaction and go up, and so on. You get my point? But what imagine that all interactions are important. People are interacting, village people are interacting with city, everybody is interacting with the prime minister. Then you need to take all the interactions. So it turns out. So I got a solution. This has not been solved by anybody, okay? So there is no solution for Burger's equation, field theory. So I tried this, saying instead of doing this, I'll sum over full integral. So I said let's try integral from 0 to infinity. Then I get a solution. Okay? So I'm saying I'm going to club. So this is in fact done in field theory as well. So instead of doing shell by shell, you do full integral, and that integral will give you the viscosity at large scale. Okay? So I did the full integral, assuming the formula for nu k squared as nu star k times mu. So it has dimension of 1 by time. And nu star is a dimensionless constant. Okay, if I substitute it here, then I can get this integral 0 to infinity. So I'm basically just saying this k by 4. This is I just equate it to nu star mu k. Okay, so this is the wave number. This is my viscosity. So that's the assumption I make here for this example, and I solve this problem. Okay, so this is something which you will not fully understand. I don't understand fully myself, but I can get a reasonable answer for this as well as for the flux. Okay, so how do I compute this one? So now assuming that we can do it, let's follow this. So this k by 4, k cancels. So dp. Now what is this? P cq. So p by q squared plus q by p squared, and the overall how much? What is the factor? Mu squared by L. So mu squared by L, and bottom will be, follow this formula, nu star mu p plus q, but mod, so these are mods. So my this should be mod. This is positive number. Your correlation should always decay, it cannot increase. Even if q is negative, should decay. That's the assumption which is made here. The correlation must always decay. So this is mod. Okay, so let's compute this integral. So here mu, so there is one mu here, one mu here, one mu here, so they all cancel, right? So this nu star square will come to the left, 1 by length, which is somewhat of a bother, but I'll get rid of 1 by L. Okay, just give me 1 minute. 4 integral dp So p squared, q squared, p cube plus q cube, right? So the p cube, and then mod p plus mod q. Okay, so assume k to be finite. K is finite, so p can be any value. So where is this integral maximum? Where does it get a maximal contribution? Q is k minus p. Okay, so k is finite. So either q can be small or p can be small. So this p squared, q squared, no? Let's say p is 0, then q will be order k, right? Coming from here. If p goes to 0, then q is order k. So what will happen? So if p is small, then I get dp p cube by p squared, and p small. So this is k. No, this is not. This is k cube. This will be k cube, no? P 0, q will be k. So k cube by p squared, and q is k squared. So I'll get dp by p squared, and in fact this k squared cancels. This is cubic dimension and this cubic dimension. So this will be dp by p squared. For p small. Rodin, okay? This cubed order and this is a fifth order, okay. So that's why I get 1 by p squared, no? So q, look, p small will be giving you k cube, fifth order. So this is this 1 by p squared. Okay, k will cancel. What is dp by p squared? Is a divergent. Okay, so this gives you 1 by p, which will blow up. So to solve this blowing up problem, what is done? If you done particle physics field theory, you will put a cutoff. The cutoff is put. So instead of 0, you put a cutoff at wave number k naught. So you put a cutoff at k naught. So what is the lowest wave number? Box size, no? Correspond to box size. So this will be the 2 pi by L, k naught, which is the box size. So that L will cancel here. So I get 1 by 4 L and 2 pi L. So that cancels. So nu star squared is 1 by 8 pi. There is a there, I think a factor, I missed some factor, but that's what we get. We get a finite value for nu star. So if the final outcome is that my renormalized viscosity nu k squared is nu star, which is that constant. I will send you this notes. This notes. My calculation shows me that nu star is 1 by 2 pi. There's a this one has also 1 by 2 pi. 1 by 2 pi. For spectrum has addition 1 over 2 pi. So if you put everything right, then nu star mu. This is outcome of this calculation. Okay, it's not an easy calculation. I don't expect you to understand fully, but This is how we solve renormalized viscosity for Burger's equation. So what did I do? So let's just go back. So I start from the equation. Then I perturbatively expand this right hand. So this is my equation, okay? But in fact, this less greater did not help me because I was not getting the right answer. This L is a big problem. For Burger's equation, this is 1 by L. I was not able to cancel it. So I said, well, I'm going to compute this full integral for all wave numbers for given k. Give me k, then I solve this full integral, and that will give me the renormalized viscosity. Okay, and that integral was from minus infinity to plus infinity. Well, it usually should be minus infinity to plus infinity, but we say 0 to infinity multiplied by 2 for even function. It's not quite even, but I approximated it. Okay, so I approximated right now. Hopefully, we'll do it exactly with Mathematica, this integral. But this I compute for the full range, and this integral is blowing up. It is divergent. So we said, well, I'm going to put a cutoff on P, lowest cutoff, because that comes from the box size, and that does not blow up. Of course, I put a cutoff, and that happily cancels that L factor. So I get my new star from that calculation, and there is my renormalized viscosity for Burger's equation. So it is a pretty tricky calculation, I think. I was struggling, but I got some ideas for this lecture. I think there are some few important ideas is to use a cutoff and don't go with Wilson procedure, but do the full integral. This is non-local, and this is also a new, key input to this calculation. It is not a local interaction. So all this requires some more thought and refinement.